was kinetics, I think. And so we're off now to really the main part of the class here, which is about equilibrium. We're going to talk about chemical equilibrium, and then we'll talk about every equilibrium you never want to know about. And then we'll be done after exam 2 and not talk about it too much more. But we will actually a little bit after that as well. So chemical equilibrium is the really main topic here of this course. And when we talk about chemical equilibrium, it's really involving a specific type of reaction that is taking place as a reaction that is a reversible reaction. If I learned the alphabet here, I think D comes after C. There we go. And reversible reactions are these guys that have basically arrows that are heading in both directions. So it has a forward direction, as we talked a little bit about, I think, the other day as well, where we have our reactants going to products. And at some point, what will happen is we will build up enough products that they will actually sort of recombine and head back in the other direction. And that is what is referred to as the reverse direction, heading in that direction there. And this process will continue until chemical equilibrium is met. Now, when people sometimes hear equilibrium, they hear equal, and they assume that it means that you have equal amounts of everybody on both sides of the arrow. And again, it's actually not the case. So when something reaches chemical equilibrium, we're actually talking more about the rate, like kind of what we were talking about in the previous chapter. And what we're talking about specifically is the rate of that forward direction will eventually reach the same rate as the reverse direction. So what happens when something reaches chemical equilibrium, it doesn't necessarily mean that you have the same amount of reactions and products at that point. It just means as quickly as it goes to make products, those guys will kind of turn around and come back the other way just as quickly. The sort of consequence of that is when it does reach chemical equilibrium, everybody gets sort of locked into place in terms of where their concentration is at that point. And if we're doing something like pressures, where their pressure is at that point. And that's because, again, as quickly as it goes that way, it's going to hop back the other way. So net-wise, there's not going to be much change happening on the left-hand side and the right-hand side of the arrow when we reach chemical equilibrium. But that could occur definitely before we got equal amounts of stuff on each side. So the first major thing to remember is it's really about the rate of those forward direction and reverse direction equaling each other. And again, it will lock everybody into place once that's reached. As long as you don't do anything to screw up the equilibrium, it will pretty much maintain where everybody's at, because just as soon as it loses a little, it's going to come back the other way, and everybody will just maintain where they're at. So when we look at a reaction that's in chemical equilibrium, if we were to look like, at the beaker or whatever it may be, to us, sort of on the sort of big level there, it may look like there's like really nothing going on, like the reaction's over, not much is changing in there. But if we look at sort of the super zoom level, where we go down to the atoms, the molecules, and everybody reacting, there is a lot of activity happening in that beaker. There's guys going from reactants to products, there's guys going from products to reactants. Again, it's just happening at the same rate, which makes it appear like, there's not much going on, it's over. But there is a lot of activity that is continuing to happen. You are continuing getting reactions converted to products and products going back again at the same rate. So again, nothing looks like, anything's happening. You could kind of think about it like, if you had like something, a cup of water or something like that, and you're able to take some water out the top, right? But at the same time, still put in some water at the bottom at the same rate. The overall level, right, of that water is going to basically maintain where it's at, right? Because just as quick as we lose, we're adding some to it. And that's sort of what's happening as it's going back and forth in the same sort of rate. Any questions on that there? So that's what we were just talking about again on the macroscopic level is static. On the microscopic level, there's a lot of activity that's occurring. So when we look at a reaction, say like this one here, which looks like the formation of ammonia, a little H2, some N2, little NH3, pop the 2 there, maybe a 3 there. So at the very beginning of this particular reaction, we can see that we pretty much have basically all reactants, and we have really no products at the beginning of this particular reaction here. And as this reaction progresses, there's really only one choice for something to happen in this case. Since we only have reactants, really the only choice is at the very beginning, we're going to pretty much have that forward direction dominating, right? So we're going to have to start to make some products. And that's what we kind of see here. We start to see a decrease in our reactants. At the same time here, obviously, we're starting to see an increase in our products being formed. At some point along the way, we will build up enough products that it will be able to start heading back in the reverse direction. So at the beginning here, we see a relatively kind of sharp increase, right, in product formation. But as we kind of make some products, we're starting to not get as of a sharp formation of our products. And that's because some of those are now going back in the other way. Same thing here. We see a little sharper of a drop at the beginning for both our reactants, right? Because they're pretty much all being fed into making our products. But as we get enough products made that it's going to come back the other way, we don't see as drastic of a drop, right? And eventually what's going to happen, as we can see in all three of them, is they are all three going to basically level out, right? And when they all three of these guys level out, that would imply that their concentration is changing or stays the same. Stays the same, yeah. And that's basically where chemical equilibrium has been met at this point right here, where they all really start to plateau out. And that means that we've hit a part where the rate of that forward reaction and the reverse reaction are going to equal each other. So we're going to not really see any more decreasing for our reactants and increasing for our products. At that point, they're locked into place. They're going to maintain. We could also see from this graph, again, getting that idea of equal out of our head. They're not equal, right, in terms of where they are in terms of their concentrations, but they're able to maintain those concentrations of where they're at when we reach equilibrium. And again, they will be able to maintain that as long as you don't do anything to screw up the equilibrium, which we'll talk about later in the chapter, things that will mess up the equilibrium. But they'll be able to maintain those concentrations. Any questions out there? All right, so initially here we have, again, in this particular reaction, we could assume that we would have no products there on the right-hand side. No H2R. Our CO2, we would mainly, again, have pretty much all reactants. So once again here, we're going to see that forward direction dominate, and then we will slowly see it sort of slow down a little bit as the reverse direction gains enough reactants to start heading back in the other direction, until once again, that rate of that forward reaction or reverse reaction will basically reach each other. And that is graphically where you could always sort of see where equilibrium is reached, is where you see, again, those guys really start maintaining their concentrations, not changes occurring. And that's when basically that forward or right direction and reverse direction will again equal each other. So if we take a reaction like the one we were just discussing there that does reach chemical equilibrium. So if we have this guy that has reached chemical equilibrium, and we decide to add more water to it, what's going to happen in terms of the concentrations of our reactants, our products? Will they get larger? Will they get smaller? Will they stay the same in this case? So let's talk about if we add water to this. By the way, the other thing we should also think about is, if we had, say, a beaker, a container, whatever it may be, and we have a reversible reaction such as this, right? We'll just assume it's all staying in this container. They're all pretty much in there, right? They're all moving around. They're all in that container. There's no really left side or right side, but we think about it as, left side, right side stuff. But, we have a little bit of everybody at this point as it reaches equilibrium, basically moving around in that container. So if I add more water to it, what would happen to the concentration of my CO? Will it stay the same? Will it get larger? Will it get smaller? Should get smaller, because when I add water in this case, I am basically adding more reactants, which means more reactants are available to start reacting, which means really in this case, I'm going to help kick off which direction of this reaction, forward or reverse? It is going to kick off that forward direction, right? Because we just got the availability of a lot more of those reactants. We're not going to have to go hunt down anybody. It's going to really force that forward reaction to occur. And because the forward reaction is going to occur, both of these guys are going to be needed, right, to make products. So we should expect the CO concentration, right, to go down. On the other hand here, the concentration of these guys, we should expect to should go up, right? Because and we should have that forward direction happening, and we should be making our products in this particular case. How about the water itself? What happens with the water? Well, the water actually will go up because you added it, right, artificially. But eventually what's going to happen, right, is as that forward reaction occurs, we then should start to see it work its way back down, right, as it's going to be needed to make products. And you may, in the case of water, for example, if you actually had numbers, you may actually end up higher than you started with, and that would only be because you artificially threw it in there to increase it. But that's sort of what you should see. Overall, you should see a downward direction for it after, perhaps it jumps after you add it, and it should make its way back down. Any questions on it there? All right, so let's take the same one, but we add H2 in this case. What's going to happen here to our concentrations? How about our water concentration? What will happen if I add more H2 to this? It should go up. And in this case, we think about it, we are adding H2, which is on the right-hand side of the reaction. And that means that should kick off the reverse direction, right? Yeah. And as it kicks off the reverse direction, really our products here are like our reactants, right? We're going to have those guys comboing to make our reactants on their side. So we would expect our CO2 to come down in its concentration, just like in the previous example. Because reaction is heading towards the reactant side, we should expect to see some increasing happening there. And once again, for our H2, we will see probably a similar aspect, artificially increased by us, but then as it starts reacting in the reverse direction, we should start to see it decrease. Any questions on the idea there? All right. So let's talk about a very important letter, and that is capital K here, and that is the equilibrium constant. So K, which is capital, different than the little lowercase k that we had there for the rate constant, that is the equilibrium constant. And frankly, this class is brought to you by the letter K. Yes, we will talk about K, all kinds of K, KC, KP, KA, KB, KSP, KF. I know I could keep going, K, you know, all these Ks here along the way is essentially what the class is brought to you by. But the equilibrium constant is a relationship of really products to reactants. So really the concentration of our products divided by the concentration of our reactants. And once again, when we do see this little bracket, that means concentration. And usually what we're talking about is our friend molarity, our moles per liter is typically what we're referring to when we see that. So if we take, for example, this equation that they have here, the N2O4 goes to 2NO2. We can take K is equal to the concentration of NO2 squared divided by N2O2, and it equals this number, which is not really relevant for our purposes or anything like that. But a couple things that we do when we do our equilibrium constant is we actually do take the coefficients into account as the exponents. So that is where the 2 comes from, is from the coefficient. And obviously the first guy there is a 1. So on the bottom there, we don't write it, but it's assumed to be 1 in this particular case. So in general, when you have a balanced equation like we see down here, you take the concentration of your products divided by the concentration of your reactants. And again, we do use the coefficients as those exponents. When we do this, this is what is sometimes referred to as the Kc value. I'm going to go with concentration for C. That seems good. It could work. So that is going to be the equilibrium constant for concentration, and it is products over reactants. Now, this is a constant number, which means it will stay the same no matter what the situation is. And what I mean by that is, let's just say, for example, we had our reaction like this, and this is another concept that sometimes is hard for people to understand. But let's just say in experiment 1, we started with 4 molar of this guy, 3 molar of this guy, nothing of that guy. Let's say experiment 2, we had like 2 molar, 4 molar, maybe 1 molar, just making up numbers, 2 molars. That guy is what we started with. And let's just say experiment 3, we had none of these guys, but we started with like maybe 2 molar that, 4 molar this. So if we let all these reactions go and we calculate the equilibrium constant for all these guys, would it be the same number or different? It would be the same, regardless of how much you start with, yeah? So regardless of how much you start with, it will always come to equilibrium, which means, again, the rate of the forward direction and the reverse direction will always come with the same proportion of products to reactants. So a simple way to envision that, sometimes people think like, I started with more of these reactants than this one, I should get a different number at the end. And again, that's not how it works. So if we take just like a number like 2, for example, and we'll say our equilibrium constant is 2, right? So if we were get this number by taking like products over reactants, which is like a fraction, right? If I take 4 divided by 2, I get what number? Right. Take 8 divided by 4, I get 2. Yeah. I take 2 divided by 1. I'm going to go easy on me on this one. This one's going to be 2 as well. Yeah. So those are all different numbers, right? And they're all different proportions of things, but the same proportion of basically our top number to our bottom number, which in this case of the equilibrium constant is products to reactants, will always end up the same. So people often think, well, I'd use more in this reaction or experiment, or use less products in this one or more in this one. I should be getting different values for the equilibrium constant. So a good way to remember that is the name is an equilibrium constant, which means it should be a constant number regardless of what you do. The one and only thing that can actually affect the value of the equilibrium constant is temperature. So if you did all these experiments, and let me explain what I mean by that. If you did all these experiments at the same temperature, say you did all 3 of these experiments at 25 degrees Celsius, and we'll just use this number, you will get 2 every time you did it, right? Now, if you change the temperature to, say, 60 degrees, right, Celsius, and you did all 3 of these experiments, maybe you'll get an equilibrium constant that will be, we'll just make it up as 10, right? What we talk about here is the difference between the equilibrium constant we had at the lower temperature, for example, and the higher temperature will be different. All 3 of those experiments that I run at 60 degrees Celsius, they all should end up with what equilibrium constant? 10, yeah. So as long as you keep the temperature the same through, say, all your runs, you should end up with the same equilibrium constant. But if you're comparing an equilibrium constant from one temperature to the next, they will be different numbers. But as long as you keep the temperature the same and you do multiple runs, you should always hit pretty much the same number. Questions on that? Yeah. Okay. So temperature is, again, the only thing that can affect the value of the equilibrium constant, but changing the amounts of concentrations that you use of reactants or products will not have an effect because, again, it will come to rest at that same rate of products to reactants. Any questions on that? So what does this equilibrium constant tell us? Well, first off, this equilibrium constant is actually just a number. Good news is they beat it to your head, units. No units on this, so just number. So what does this number tell me? If I have a really large value, or if I have a large value for the equilibrium constant, that means when I reach equilibrium, what should mainly be there if I have a large value for K? It should mainly be products, right? If we just think about it mathematically, we're taking products divided by reactants, which means If I have a big number for K, I need a big number up on top, right? So big number divided by a small number gives me a big number. So if you see a value of K that's a large value or considered a large value, that means when you reach equilibrium, you should mainly have products present. And vice versa, if I had a small value for K, that should mean when I reach equilibrium, I mainly have reactants left. And again, same mathematical here. In order to get a small number, I need a small number on top divided by a larger number on the bottom, which would mean I have mainly reactants. So the sort of value of the equilibrium constant does tell you, what you should expect to sort of be there at the end of the reaction in the sense of equilibrium being reached. Should you mainly have reactants? Should you mainly have products? So what is considered a big number? Well, it is that big number of 1 is considered a big number. So if you have an equilibrium constant that is essentially greater than 1, positive exponent greater than 1, it is considered large, which means you would mainly have products being favored. And vice versa, if you have some type of equilibrium constant that is less than 1, then you would expect to mainly have reactants. Now, there is obviously degrees of that number. So you can have an equilibrium constant that is like huge, like to times 10 to the 34, right? Which is a very large number, right? And what that essentially means is pretty much it is a reversible reaction, but pretty much it's all heading in that direction. It's almost a one-way street, but it will still, because it is a reversible reaction, head back the other way a little bit if you have a super large number. And just like you could have a really large number, you could have a really small number as well. So you could have like an equilibrium constant like times 10 to the minus 34, which is a super small number. And if you have one like that, that's going to mean that basically you're going to basically stay over there on the reactant side. Not much is going the other way. So, and there obviously are various degrees in between of all those numbers as to, what you look at. So there are some where, we'll do some calculations later on the semester where we go, well, this thing is really large. So we're just going to kind of assume it's all going, that way. Or this thing's really small. So we could assume we're not really making much products. We have basically reactants hanging out there. So the sort of value that we see on certain equilibrium constants does play a role in sort of how we do some of the math and calculations a little bit later on. Any questions on that? So here we have Mickey. He's happy. And then he had a long day at Disneyland. He went upside down there. But more importantly here, we have the special Halloween going on right now, right? It's a long night. So we have the equilibrium constant, which is 25. That means when we reach equilibrium, reactants, products, what should we have here? We should mainly have products as 25 again is greater than 1, which is considered a large value. So then we would mainly expect Mickey that had a hard day to be there when we reach equilibrium. So let's talk a little about equilibrium and a couple of things. And first off, let's talk about homogeneous equilibrium. Homogeneous equilibrium is the same idea as like a homogeneous mixture, which means everything looks the same throughout. And basically what that means is you have an equilibrium where everybody's in the same phase. So everybody's in the same phase. And we could write our equilibrium constant here like we talked about. Taking our products, once again, taking the coefficients as our exponents. So that'd be our concentration of NO2 squared over our concentration of N2O4. Once again, the coefficient here is 1, which is why there's nothing written there. Again, it's assumed to be 1. And that's the Kc value, as we talked about, C meaning concentration. But in this particular case, we're dealing with gases, right? And gases make you think about pressure, makes you think about PV equals nRT, right? That is our ideal gas law that we talked about, right? Pressure being atmospheres, volume being liters, moles, or gas constant. And our temperature. So in a situation like this where we maybe have gases happening, we may actually be looking at sort of pressures or falling pressures and stuff like that. So we could also write an equilibrium constant that actually deals with pressures. So if you have sort of an equilibrium where you got gases happening there, you could write an equilibrium constant where this is the partial pressure squared, once again, using the coefficients of NO2 divided by the partial pressure of N2O4. This is creatively called Kp. I'm going to go with pressure on that one, as the other one deals with concentrations. Technically speaking, not necessarily this application here, but later on, when we talk about really the heart of these type of calculations, if you're dealing with pressure, typically the standard unit of pressure that you should use in calculations, and we'll talk about later on in a bit, but is atmospheres is typically the unit that you use. A reminder that 1 atmosphere, right, is 760 torr, right, or 760 millimeters of mercury, right? Not too critical here, but usually atmospheres is kind of, if you're doing some type of equilibrium calculation, you want to make sure that they're kind of in atmospheres. Even if they kind of give it to you some other unit, you usually want to convert it to atmospheres, do the calculation, then convert it back to whatever unit you're looking for. Now, in a lot of cases, the Kc value and the Kp value will not necessarily be the same numerical value. So they may not be the same numerical value, but they will tell you the same thing, right? So if I have a large value of Kp, that means I should mainly have products, because the only way to have a large value of Kp would be I need some gases on the product side to have a lot of pressure, right? So if I don't have much gases on the product side, or didn't make a lot of the gases on the product side, I wouldn't have very much pressure happening over there. So obviously it means the same thing. And if you have a small value of Kp, again, it means you pretty much have reactants when you reach equilibrium there. So there is a way to go between these two, which is going between Kc and Kp. So in certain cases, you may be given just the concentration of stuff, but maybe you're interested in what the Kp value is, and vice versa. You may be given some partial pressures at equilibrium, and you may be interested in what the Kc value is. By the way, either one of these, the Kc or the Kp value, in order to actually put numbers in there, right, to get actual values, they do have to be both either equilibrium concentrations when sort of the reaction reaches equilibrium, or they have to be what the pressures of everybody are when they reach equilibrium. So you can't throw initial concentrations or initial pressures into these. They would have to be equilibrium pressures or equilibrium concentrations to do so. So we can calculate this by Kp is equal to the Kc value times RT delta N. So the R here is our gas constant, the 0.08206 version, or 21 if you like that, that's okay too. T is our temperature in Kelvin. Remember gas law, so Kelvin on that. Our delta N is the change in the number of moles of gases. And that should be products minus reactants when we calculate that. And that's really important. So for example, if I had 2A goes to B, delta N in this case would be I heard -1, I heard 1, I heard 42. No, I didn't hear 42. But these are moles, right? It's like you did stoichiometry, right? The coefficients, the mole relationship. So we would want to take actually products, which in this case is 1 minus 2, which would be -1, right? Now, does it really matter if it's -1 or 1? It does in the math of it, right? So if I look at my equation here, especially this part of it, if I took this to the 1 versus this to the -1, is there a difference mathematically? There is, right? The guy on the right, you're going to do 1 over it, right? And so it's really important to make sure that you do products by reactants, because if you do get a negative, it's going to obviously affect the math part of it. So sometimes people make a common mistake. They just kind of take the difference and not worry about, did I do products minus reactants versus just taking the difference of it. So always do products minus reactants. If you get a negative, again, that will affect obviously the calculation that you got going on. So this is the formula that we can use again to go between the two, Kp and Kc. And like I said, sometimes you may be given just one piece of information or no one piece of information, pressures versus concentrations or concentrations versus pressures. and you may want to calculate the opposite there. All right. Now, when we write an equilibrium constant, there are a couple of things that are actually sort of constant. So for example, when we write the equilibrium constant expression for this reaction, which is a little acetic acid plus some water, acetate, and some hydronium ion, we would do our products over our reactants. Now, the overall concentration of water, which is really the basis of all this aqueous stuff, right, is pretty much going to remain constant overall because it's not going to change that much. And because it's going to remain constant, we do not include it in the equilibrium constant. So the proper equilibrium constant for that equation is actually this, where we take the acetate times the water, times the acetate times the hydronium ion, H3O plus, divided by our acetic acid. So once again, our products divided by our reactants. In this case, the coefficients on everybody is a 1. So that's why we have obviously nothing, squared or anything like that. Now, in general, there are two things that are not included. Yeah. Good. Oh, I'm sorry. Am I hearing things? I might be just hearing things. Oh, I'm sorry. Okay. Yeah. I heard professor. I'm like, oh. Thank you. I'll take the bless you too. All right. So two things that are not included. It is Thursday, right? It's almost the weekend. All right. So two things that are not included when we write the equilibrium expression is things that are pure liquids are things that are actually solids, as we'll talk about in just a second. So both water, obviously water is a pure liquid, and anything else that's actually a pure liquid will have such a high concentration that it pretty much will remain constant over the whole of the experiment. And anything that's a solid pretty much will not do much in terms of the equilibrium or reacting because, frankly, it's a solid. It's like threw a rock into the beaker. It's just going to kind of sit there, right, and not do much. So it's not going to really participate. So really what that means is when we write equilibrium expressions, there's really two things that are included, and that is things that are aqueous and things that are gases. So these are really the two things that you want to include when you write the equilibrium expression. You want to leave anything that is a pure liquid, anything that is a solid out of it. The only way really a solid could participate sort of in the equilibrium is it would have to dissolve, right? And once it dissolves, it is no longer a solid, right? It would be aqueous at that point, and then it would be floating around ready to participate. Those two things that are aqueous, things that are gas, they're moving around, they're free, they got a lot of energy, they're ready to go and to react, and that's why they affect the equilibrium, as opposed to, again, a solid, which is just going to kind of sit there. And again, a liquid will have, pretty much a constant, not much is going to happen with this concentration. All right, so write the Kc and Kp if possible for each of these reactions. Yeah, let's take a look. We'll start with the first one here. We'll do our Kc. So that's again going to be our concentration of our NO2. Once again, we do see a 4 there, so we do need to take it to the 4th power. We're going to times it by our other product, which is O2, and again, our coefficient is 1, so we don't need anything up there. We'll divide it by our reactants, which will be our N2O5, and we're going to square it because of the coefficient. And that's it. I think I'm running out of things. So that's our Kc. In this case, we do have some gases here all the way through, so we can write a Kp, and it basically will be the same thing, except it will be the partial pressure of NO2 to the 4th, the partial pressure of O2, and our partial pressure of N2O5 squared. Any questions on either of those there? Looking at our bottom one here, we're going to do our Kc, which again will be our product. So our H3O plus times our F minus divided by our HF. And what about the water? Am I including it? I am not. Again, it's a pure liquid, so it would not be included. Can I write a Kp for the bottom one? No, there's no gas, so it makes it hard to find pressure. Yeah, so you need gas to be involved. I would say typically probably they'll all be gas, or you'll have solid and gas sort of combination is probably commonly what you would come across. But you definitely would obviously need some gas to have some type of Kp expression. Any questions on those? Okay. All right, so then let's try some calculation here. The equilibrium concentrations for the reaction between carbon monoxide and chlorine. Concentration is 0.012, 0.054, and 0.14 molarity. What are the equilibrium constants, both Kc and Kp? We are given concentrations. We're looking for Kp and Kc. It would make sense to solve for which one first?
The constant.
Yeah, Kc, since we do have the concentration. So we'll start there with our expression. Our Kc is going to be the concentration of COCl2 divided by CO and Cl2. Obviously, these are some equilibrium concentrations, as I mentioned, so we could go right in there with no problem. So we got a little 0.14 action, 0.012 and 0.054. Gonna hit you a 216, or if you're still a sig fig fan there, 220 on it as well. No units needed, right? Because it's an equilibrium constant, so we don't have to worry about those. So that's all good. By the way, this would mean we mainly have reactants or products as well. We should have products. Again, that's a fairly large equilibrium constant value. So we should mainly have products happening at that point. Now that we have it, we could use that other formula that we had earlier to go between our sort of Kc to our Kp value. And that was the one that was our Kp is equal to Kc, a little RT delta N action. Our delta N, speaking of that, is going to be on the product side. We have 1, which is just coefficient, right? Minus 1 there, and 1 there is 2, gives me a -1 happening there. And again, important, as we talked about, the products minus reactants, because that negative is going to affect our calculation. We got to do just maybe one more thing. We got a temperature value, right, that does need to be converted into Kelvin. So that's a 74 plus a 273, and that will get us 347. Sounds good. 347 Kelvin. All right, now we have everything we need. So we'll do a little Kp is equal to our Kc. I'll use the 220 since I boxed it or circled it. Times my R, which is 0.08206. And once again, you can use 0.0821 if you like. Times our 347, and once again we're going to do to the -1. So you do want to clean up what's in the parentheses there first, and then take it perhaps at a -1. So 0.08206 times 347, and basically 1 over that number, and times it by 220, and we'll end up with something like 7.7. I think maybe you get 7.6 if you took the 216 number through there as well. So a large value for Kp. It is, yeah. So it tells us again the same thing. It tells us that we should expect mainly products at equilibrium. Again, they're not numerically equal to each other in a lot of cases. They won't be the Kc and the Kp, but they will give you that same piece of information about what you should expect to sort of be there when equilibrium is reached. Any questions on the calculation? Yeah. It doesn't. So any K value that you have typically will not have units. I've only seen one person in my life write units on it, but you usually don't write units, and you shouldn't write units. And it's really because a couple of things, they really don't end up canceling out nicely. And so you'll end up having different units, you know, kind of depending on what you got going on in the calculation. So most of the time, equilibrium constant, pretty much 100% of the time, is going to be just a number, no units associated with it. Other questions? All right, which makes it easy. You could do a little lazier calculation with not so much units in there, huh? I suppose. All right, so you can still put the units just at the end. You really shouldn't have units associated with it. We have another one here, a little NO2 going to NO and O2. Got a Kp value in this case of 158. we're looking at what the pressure is for oxygen, and we got a partial pressure of NO and a partial pressure of NO, which seems wrong. So why don't we just randomly go with that one as NO2 and hope for the best? There you go. You don't have it on your. Okay, let's take a look. So obviously we're dealing with pressures, so Kp would be a good expression to start with. So we're going to do our products here. So partial pressure of NO, and again, we're going to square it because of the coefficient. We're going to multiply it by our other reactant, which is O2. And again, here the coefficient is 1, so we don't have to do anything to it there. We're going to divide it by the partial pressure there squared of NO2, again, because of the coefficient that we see there. In this case, it actually gave us the value of 158, so that would equal 158 in this case. So we do have some pressures given to us. We have NO2, and we also have NO, so we can take our NO, and we got our pressure of O2, and divided by our NO2, which would be 0.4. And we do need to square it, just like we need to square the guy on the top as well because of the 2 that's there. And that's going to equal 158. So mathematically, right, we're going to multiply the bottom to the other side, and then we're going to come back and divide by what's up on top, right? So I'm going to do that all one step here on my calculator. So I'm basically going to take 158 and times it by 0.4 squared, which I think will get me something like 25, 28. And again, now we're going to divide that again to the other side. And we're also going to make sure we square it as well. So divided by 0.270 squared. Going to give me, we got 347, we'll call it. Do I need a unit on this one? I do, because it's a pressure, right? So the unit should be the same as everybody else. So this is going to be 347 atmospheres. So question on that calculation there. We could also think about, does that make sense? So, well, maybe it does. The value of K is what here in this case? 158 is pretty large, yeah, which means it's pretty much a one-way street, right? Which means it's heading towards the products, and that guy is a product, so it would contribute to most of the pressure that we see there in that particular case. So in that sense, it makes sense. That's tremendously high pressure, right? That's like a real gas type pressure type of situation. Yeah. Other questions on that? All right. So a heterogeneous equilibrium is one where we do have things in different phases. So we kind of jumped a little bit earlier on this, but again, if we were to write the equilibrium expression for this equation and just do it like normal products over reactants, we will once again have a solid that's involved, which again, as I talked about earlier, really won't participate in equilibrium because frankly, it's a solid. And again, the only way for it to sort of do that is to change out of the solid state, which then it would no longer be a solid. So the actual Kc expression for this would be the concentration of CO2. And we could also write a Kp for this one as well, which would be the partial pressure of CO2. And I forgot to circle this guy as well because he is a solid as well, which is why we did not include that one in there. Yeah. It is. So what this just means is, in this example, the way they did it is, if you were just going to write the equilibrium expression like normal products over reactants, that's what you would get. But because these guys are constant, you should kind of cross those out to give you the real equilibrium constant, which is what we got on the bottom there. So outside of this slide, you probably won't see that too much anywhere else. But they were just using it to emphasize the fact that, you know, if you did it like normal, you should then go and take those out to get to the proper equilibrium constant, which is the 2 on the bottom there, which would have just CO2. Now, what would the equilibrium constant expression be if I had, say, something like, I don't know, let's just say something like this, just made up, what would the equilibrium expression be? Yeah, you would do 1 over the concentration of A in this case, would be our K, because obviously we have nothing there, so you just do 1 over that. Question on equilibrium constants here, how to write them. So again, no liquids, no solids, just aqueous and gas go into our equilibrium expression. So you could do calculations. Again, as you can see here, not much happening in terms of our solid, but our gases obviously can get involved in there. Let's try one more here. Consider the following equilibrium at 295 Kelvin. The partial pressure of each gas is 0.265. Okay, so taking a look here, obviously in this case, we do have the pressure given to us, our pressures. So KP would be a good place to start. So we'll do our KP, which in this case would be the partial pressure of NH3 times the partial pressure of H2S. Once again, we will not include that, right, because it is a solid. And since they are both the same pressure, in this case, we basically got 0.265 squared. That's going to give us 0.265 squared. It's going to get us something like 7.02 times 10 to the minus 2. In that case, will be our KP value. Any questions on that there? We then can use our, they don't, but they are a K value, so there is no units, which is essentially why there are no units usually with K values, because they really don't cancel out. You would end up technically in this case with atmosphere squared, right? In this case, you just assume there's no units, and that's why I was saying earlier, it's really why they don't have units associated usually with the equilibrium constants, because they really, in a lot of cases, won't cancel out. And sometimes you'll get some different units for different ones. So to make it more of a constant sort of value, and it's just a number that we associate with it. Yeah. Because in the case of this, for example, it's really just the numerical value that is what's going to basically tell you the importance of it is, do you have a large value or a small value, rather than in other things where, it's important to know that I need 40 grams of this versus 40 pounds of it, right? So that's, that's a more important sort of place where you need it now. Other questions? Yeah, so again, it matters in terms of units if you're given something that is not an equilibrium constant value. So like the previous problem, we were given a pressure. So it does matter to say that, all the other pressures were in atmosphere. So clearly this one would be in atmospheres as well, as that number would be different if we were talking about something that was torr or millimeters of mercury and stuff like that. So if you're given anything other than an equilibrium constant value, you do need to obviously have the units. But anytime you solve for anything that's K, you don't need them. Other questions? Okay, so our KP is KC RT delta N. So delta N in this case going to be our products, which is 2 minus 0 in this case, right? As we have one gas there, two gases, and no gases on the side. Our temperature is already in Kelvin, so that's nice. So we're good to go on that. So in this case, we got something like 7.02 times 10 to the minus 2 is equal to our KC, which is what we're looking for. Our 0.08206 times our 295 that we're going to square. So again, here, I'm going to get a number here, and then I'm going to divide it to the other side. So we're going to take 0.08206. We're going to times it by 295. Then we're going to take the square root of it, by the way. Sometimes people want to square root just the temperature and then times it. Yeah. So you got to times the two values inside first and then take the square of it. That gives me something like 586-ish. I'm then going to send that to the other side and divide the 7.02 to the minus 2 divided by that. And that will give me a 1.20 times 10, 1, 2, 3, 4, negative 4 here. for my Kc value in this particular case. Any questions about there? That would mean in this case, we would mainly expect reactants or products.
Yeah.
That's both answers, but yes, it would be reactants there at the end. And again, because those would both be considered small values of K. And once again, we do see that, and it's typical. It is occasionally possible that they could be the same numerical value, but in most cases, they're not going to be. But they do still tell you again the same thing. They're both considered a small value of K, which means we should mainly have reactants at equilibrium. Any questions on these calculations? Yeah. The coefficient in the balance equation, if that's what you're asking, is 1 in that case, but it's not included in the equilibrium expression. So anything when you look at an equation or reaction and anything that's labeled as a solid or a liquid, you just don't include it. So it's essentially thought of as like 1, basically. It's not going to really affect anything in the equilibrium and stuff like that. So we just don't include it in there. Yeah.
For delta N, are we just looking at the sum of the moles of the products minus the sum of the moles?
Yeah, so basically the total of all the gases you got on the product side and the total moles of gases you got on the reactant side. Yeah. So in this case, we basically have 2 separate gases. In a previous one, maybe we had 2 together with the coefficient. So you do have to take coefficient into account. So the easiest way to do it is just count the coefficients that are G's next to them, right? So if you have you know, say for example that was a 2, we would then have 3, right, and stuff. So you can just count the coefficients and stuff like that. As long as it says gas, sometimes people just go on autopilot and just assume that's a G and it's not, right? So make sure it is a gas when you do it. Other questions? All right, so let's talk about some other things that occur when we're dealing with equilibrium constants and sort of ways that we may need to manipulate equations. Now, there will be times where you may need to add different equilibrium reactions or equations together. Again, very similar to kind of what you do with Hess's law, sort of adding reactions together. But we do something different in terms of the equilibrium constant than we do when we do something like delta H's and kind of put them together. So there are different things that occur. If we have our first equation here, and we take our equilibrium constant expression for it, it will look something like this, C times D over A and B. If for our second equation here, we will have this for the equilibrium constant that is there, and that will give us our EF over CD. If we were to add both of these equations together, we will get an overall reaction of A plus B goes to E plus F. And much like we talked about with mechanisms and stuff like that, again, anything on opposite sides of the arrow can cancel out or reduce down. And everybody on the left-hand side of the arrow should stay there, and everybody on the right-hand side of the arrow should also stay there as well. And if we were to write our equilibrium expression for this guy, that would be K is equal to E times F, right, divided by A times B. So essentially how we get that is we take these equilibrium constants and we multiply them, not add them, which is a common mistake. So if we multiply these two expressions, right, C and D will cancel on both, and we will end up with EF over A and B. So if you find yourself in the need to add a couple of equilibrium expressions or equations or reactions together to build like an overall reaction, what you do with the equilibrium constant is you actually multiply them together. You do not add them. So again, that's a super common mistake because people think about Hess's law and the delta H's and you just add everything together. So add two reactions together or equations, and you got K values for each, and you want the K value for the one you get at the end. You multiply them together. If you have 3 of them, you multiply all 3 of them together, right? So that's basically what you would continue to do. Any questions on that arrangement there? Now, also sometimes what might happen is, again, we may need the reaction not the way it's written. So we may need maybe not those guys being reactants, but maybe we need them on the product side and our products on the reactant side. And essentially we may need to reverse a particular reaction. So if we do that, for example, this one here where we have N2O4 goes to 2NO2, and we do our products over reactants, we get 4.63 times 10 to the minus 3. Now, if we reverse this reaction, which is basically taking 2NO2 going to N2O4, what happens to the K value is it actually becomes 1 over the K value. It's not change the sign like we do with delta H. So this actually becomes 1 over the K value. And that's because they are opposites of each other, right? So it's basically 1 over to flip it around. And you would take 1 over the K value, which in this example would give us 216. When we see a K value that is given for a particular reaction, it should be for the reaction exactly how it is written, which means whatever is the reactants and whatever is the products. So if I say this reaction has a K value of 216, I am specifically talking about this reaction written like that, with the NO2 being the reactants and the N2O4 being the product. If I say it has a K value of 4.63 times 10 to the minus 3, I am specifically talking about that reaction the way it's written, where the N2O4 is the reactants and the NO2 is the product. So when you state an equilibrium constant value for a particular reaction, it should be stated for exactly how it's written, and obviously, as we talked about, at the same temperature, as otherwise it would change. Any questions on those manipulations? So also a very common mistake that people make is, again, they fall back to the delta H where they go, oh, cool, the K is just the negative value of it and just change the sign or something like that. So it is 1 over K if you got a reverse reaction. If you add multiple reactions together, you need to multiply the K values together. Let's talk about a couple other things that we may have to do to these to a reaction. Let's say we had A plus B goes to C plus D, right? And if we write our equilibrium expression here, that would be C and D divided by A and B. But as you may know, what happens if I don't need just one A, but maybe I need 2 A's in this case, which means I need to multiply this entire equation by a common number, like 2, for example. Yeah. The K expression, if I write for this equation, is now C squared, right? D squared divided by A squared and B squared. What is the difference between these two K values? It is the squared, right? I multiply by 2, I need to square the K value, not multiply the K value by 2. Also super common mistake, yes. By the way, if I multiply by 3, what should I do with the K value? To cube it, yeah. So basically, whatever number you need to multiply by an equation by, you basically take the K value to that number. So if you're going to multiply, you're going to take the K value basically to that number you multiplied by. And with that being said, sometimes you may have or start with maybe the 2A, 2B reaction, and maybe you just need one of everything, right? So if I were to go in the opposite direction, right, from here to here, I basically divided everybody by 2, right? And when we think about, I feel like I'm going to tell me what I'm saying in a second. When we divide everybody by 2, as we go from this K value expression to that K value expression, the difference there is the square root of it. Yeah, so because I divided by 2, I would take the square root of it. And just like if I divided by 3, I would take the cube root of it. Yeah, so if you have to divide by a common number, you basically take the root of that number, basically whatever it may be, going that way. So those are very common ways that we sometimes have to manipulate equations to get to an equation we're looking for. This would obviously be a situation where you have multiple equations given to you with multiple K values, and you're looking for like an overall reaction kind of built off of all those equations together. Any questions on that there? Let's take a look at one. Let me see if I can make up one and see how I do. Let's see. All right, let's say that we have this equation, A plus B goes to 2C plus, we'll go with 2D. We'll say the K value is, how about 15 today? Why not? All right, and we have another one, which is C plus D goes to E plus F, and we'll do the K value of, and we'll do a smaller number. Why not 1.125 and see how we do. All right, so we got that, and we want to get to this reaction of 2EF, 2E plus 2F. Go to, we'll go with A plus B. What is the K value? All right. Okay, so let's take a look and see. So as you might remember from Hess's law, maybe you were taught, don't make it too complicated, right? So let's just think about it logically here. We basically need to build out these two equations to end up with this equation. So very simply, I see A and B in the first one, and I just need to make sure it's on the correct side, right? So it's on the left-hand side in the top equation, but ultimately I need it on the right-hand side. So I do need to reverse the first equation. I also need one of each of those, so that's going to be okay the way it is. So really all I need to do to the first one is just reverse it, which means I would have 2C plus 2D would go to A plus B. I also need to keep track of what I just did. Now that I reversed that reaction, it means that it's going to be 1 over the K value, right? Not change the sign. So it should be 1 over 15 is kind of what we got going on for that one. Any questions on that there? Next, I have C and D, which is not in the final equation, so maybe I'll look at E and F. And I have E and F, which is in the final equation, but once again, it's on the right-hand side here. I need it on the left-hand side here, and I not only need on the left-hand side, I actually need two of them, right? So I need to actually do two things to this. I need to reverse this reaction and also multiply it by 2. Top one I just reversed, obviously. So I'm going to reverse it and multiply it by 2, which means I will end up with 2E on the left plus 2F on the left goes to 2C on the right and 2D on the right. Now I did a couple of things here, right? So I reversed it there, which means I got to go 1 over the K value. I also multiplied it by 2, which means I then need to square it as well, right? So again, you want to kind of keep track of everything. I'm out of equation, so hopefully I did this right. So let's see. We should end up with 2C and 2C canceling. 2D and 2D will cancel as they're on opposite ends. We'll end up with 2E plus 2F goes to A plus B. So that's good. I am now going to, maybe I'll get some answers here. 1 divided by 15. Gonna get us, 0.06667. We're going to do 1 divided by 0.125. Then we're going to square it. Going to give me maybe a 64 in that case. To get to this here, we'll call this K1, K2. I need to find K1 times K2. Again, not adding in this case. So that would be 64 times my 0.06 number, I think. Going to give me a K value of, we'll call it 4.3 in this case. Any questions on that? So again, you will have to do this to be able to do it. And those are really super common mistakes that people make because, again, I think it's just I remember doing this like in Hess's law. I'm supposed to like multiply and change signs, but equilibrium